Now that I've drawn my influence line, what do I do with it? Right? Notice that the influence lines that we've drawn so far and what we're going to reference are a moving, concentrated, I don't know what that was supposed to be. Concrete? I don't know. Concentrated load. Calculate a support reaction, or a force from the ones that, this is a moving concentrated load on a simply supported beam. Just a reminder, check your units, right? So based on what we did previously, where we calculated a moving concentrated load along a simply supported beam and the influence of it on the vertical reaction at one of the supports, the shear at a location, and the moment at the location, these are ways to then use that influence line to calculate if I put it here, what's this value? If I put it here, what's this value? So this was the vertical reaction at A, influence line. If I wanted to know, right, if I wanted to put the load at there, my value, my vertical reaction would be my load times this value here, which is 0.2. If I wanted to put my load I don't know. I wanted to put my load at here. That would result in a vertical reaction of 0.8 P. . sorry, concentrated unit load, right? Similarly, if I want to look at the shear force at C, let's go to the same spots. If I put my load at 0.8, then my shear at C would be 0.2 P. If I put my load at 0.2, that results in a shear at C of negative 0.2 P. Where would I place my load for the maximum positive shear? Right, I put it and put it like just to the right of C. Let's see, let's make that green. Maximum positive shear at C. If I put it just to the left, maximum negative shear at C. I should have made that a different color. If I put it just to the left, I get maximum negative shear. Finally, I'm going to look for that moment. This over here is really P times L, so again, if I put my P at 80%, I get a moment of D of 0.1 P times L, right? .1 P times L, or 1/10. If I put it over here, I'm actually going to get the same thing because this is symmetric. That results in a moment of D of 0.1 PL. Alright, essentially this axis is P times L times whatever that number is. Where would I put my load for maximum bending moment at maximum positive bending moment at D? I put it right there for maximum positive moment at D, which would be PL over 4. So this entire time we have concentrated on concentrated loads. So what do I do if I have a distributed load, right? A train, a spread out semi, if you don't look at the axles, right? What if my load is not concentrated and it's distributed? So I wanted to do this little tutorial thing right here. So let's look at my vertical reaction at A, the influence line for a distributed load on simply supported beam. This is for my vertical reaction. And I have a distributed load though, so I'm gonna apply a very small force, right? That value of my distributed load times a small width dx. And I realized that that would result in an AY of df times that value, right? If this is my P and this is my value of my influence line, right? Y. My df is P, right? That's what I just did. I did my P times that value. That would be my reaction at A due to that load at that location. Okay, now I'm going to apply a second load. Yep, if this is Y1, right? This is 0.1. My df is actually still the same because the width is still the same and the applied load is still the same, but it has less of an influence on my reaction at A. It still has some influence though, right? I'm using superposition here. I can add stuff, right? Add stuff together. Now my vertical reaction at A is df times y2 at that point 2. Again, df is equivalent to my applied concentrated load P. I have another spot. Oh, same exact right? All of these df's are equal to each other, but the influence is decreasing because I'm getting further away from that support. So if I apply these three loads, the one that would contribute the most to my vertical reaction at A is the one at 0.1. The one that would contribute the least to that vertical support reaction value is the one at 0.3. Finally, if I get really, really far away, I can add just a little bit more support reaction. You might see where this is going, right? If I keep adding, right? Oops. This is y at 4. Again, these but influence on AY varies by location. I realize I'm using Y. I'm using Y as the Y-axis, not the vertical direction. Ignore this stuff down here. It should be like to there, and to there, and to there. This is x2, x3, x4. So now I'm gonna add some more little concentrated loads, right? And I'm gonna add up their influence on my vertical reaction. What does that look like? That looks like area under AY influence line. Yay! Right? Again, my values that I'm adding are the same, but their influence on the vertical reaction A decreases as X increases. So I'm going to go back here and summarize what we just saw. Basically, if Y is my influence line value, then my vertical reaction is equal to the area under that curve times, right, this is df, df being these little babies, right? And df is equal to that applied distributed load value dx, right, that width, then the influence on my vertical reaction at A is the value of that distributed load times the area under that influence line. So if I wanted to get the maximum vertical reaction at AY, I would apply a distributed load over this entire length because that would give me the largest area. If I only applied it to, alright, if I only applied it to this part, my reaction at A would only be that area. Let's look at the shear force at C. This is what we just determined earlier, right? The influence line for that shear force of a simply supported beam subjected to a moving concentrated load. And earlier I said, where would I put my concentrated load for my maximum shear at positive shear? I'd put it right there, right? If I put it just to the right of C, I'd get my maximum positive shear. If I wanted to get my minimum, I'd put it just to the left. Right. Maximum negative shear or minimum shear. Where would I put a distributed load for my maximum shear? I'd put it over this entire length, right? Because then I would have 1/2 times, I don't know, 0.6, whatever that value is, 0.6, it's 2/3, 0.66, right? Times the length, which is 2/3. Where would I put a distributed load for minimum? I'd put it on the first third, right? Maximum negative shear or minimum shear. So that's how you can use influence lines to determine distributed loads. Now let's do a couple examples. We're going to use the Mueller-Breslau principle to draw our shapes, and what we just learned to figure out where we would put the loads. So draw the influence line for the vertical reaction at A. This is going to be qualitative, not quantitative. So if I wanted to make, if I want the vertical reaction A, I'm going to apply AY. And what would my display shape look like? It'd kind of be like seesawing over here. Right. There's my influence line. So where would I put a concentrated force? What did I use before? Where would I put a concentrated force for my maximum? Okay. Where would you place a moving concentrated force for maximum upward reaction? Probably over here. Right? Because this value looks a lot bigger than that value. Oops. Maximum upward reaction, right? And this is positive and this is negative. What about if I had a negative reaction? Downward reaction. Negative? And put it over here. Alright? Where would you put a moving distributed load for maximum upward reaction? Right? From the end over to that roller. Maximum upward reaction, distributed load. If you wanted a downward reaction, so in the opposite direction of the applied force, so we're going to come up with a different color. Orange, sure. Alright, think about it. Let's see. What would be my display shape for this this concentrated load, right? Probably be something like, oops. Something like that. So this one would probably be something like that. Over here, it's holding it, it's applying right. An upward force over here. Applying a downward force. It's keeping it down, right? If I think about these ones, let's see. I don't know. Something. It's applying an upward reaction force. If I look at this, it's probably keeping it down again, so next one, why don't you guys take a second and draw it and think about where you put the loads. Okay. Hopefully you've had a chance to look at this one. There's a third one too. Let's look at this. So shear. I'm gonna break my thing right here and I'm gonna apply a shear to that half and a shear to that half. So if I do that, I'm going to end up with a displaced shape that looks like that. And on the other side, a displaced shape that does not look like that. That looks like that, basically. So that's my influence line, right? Oh, didn't go further enough. Okay, let's see. Right. So where would I put a moving concentrated force for my maximum positive shear? I either put it right here, right, because that's my maximum positive, or right here at C, right? Depending on what those values were. This is where you need to actually have numbers. Right now it looks like the one over on the cantilever is maybe bigger, but maybe not. Maximum negative shear. Right, here's my negative or my negative. So I'd either put it here this one was actually technically just to the right of C, right? This one is just to the left of C. Again, depending on what values are actually associated with. Yep. If I had two moving loads, I would put one at one point and one at the other point. So negative shear, maximum positive shear. Oops. What about a distributed load? Let's say I go purple and then orange, right? Okay, let's see. Purple. Where would you put a distributed load? Maybe here, maybe both. All of these, you need some type of values, right? This is point C. Or maximum negative shear, I would put one here up to C, or here. Alright, this is my W naught. I don't know, I'm doing a W naught. Maybe they do that in the book. I don't know. So again, all of these depend on the values, right? Maximum positive shear. So or here with that one. Right, if I put those distributed loads over, oopsies. If I put a distributed load over this area, it would result in, over this length, right? It would result in this area times W naught as a positive shear at C. If I put it here over this length, it would result in that area times W naught as the positive shear at C. And finally, let's see if we have a moment at C. What I'm going to do is I'm going to put a hinge right at C. I'm going to, if I want to draw this moment, I'm going to apply an angular moment, right? It would result in a, draw the influence line for the moment at C. I'm going to make this a hinge and apply a moment, and it would result in a displaced shape like that. Right? So that's my influence line. Where would I place a moving concentrated load for maximum positive moment? Well, maximum right there, right? Oh wait, I just did this wrong. Somebody say, hey, you did this wrong. I did it wrong. I forgot about my supports. I was thinking of a simply supported beam and not with overhangs. Right. Be like that. Or like that. Pretend this is 0 right there. Alright. My maximum, if I wanted to apply a moving concentrated force for maximum positive moment, right there at C. Maximum negative moment, that's my maximum values, right? So, and maybe I would apply both. Maybe this one over here on the right is bigger. You have to figure out those values. That's why you can't just do this qualitatively. Where would I apply a moving distributed load for maximum positive moment? I'd apply it along this length because that would be the area of my maximum moment. So I would apply it along this length between the two. What about maximum negative moment? Oh, probably over on the outer edges. That would result in a maximum negative bending moment at the point C. And these are, again, maybe easier to see. What would our displaced shape look like? I applied this, if I look over this concentrated load, if I applied it at point C, I would have a display shape that kind of looked like that. So yeah, I'm going to have bending moment maximum probably right in the middle, right there at C. If I applied these two loads on the outside, my display shape would look like that. Now I have negative bending moment, right? It's frowny face. Frowny face. So at C, I have maximum negative bending moment. Similarly, gonna have some type of happy positive moment if I apply a distributed load between the two supports. And sad negative moment if I apply it on the two cantilevers. So that is how you can use your influence lines to determine where you would place a force or distributed load for maximum effect, right? If I wanted to find the maximum influence on a certain thing, on a certain value, where would I place my loads? Because then now I can use, if I wanted to find out what that bending moment was, say here, right? I would use this loading to find my design moment for my moment at C. Yeah. Okay, so that is influence lines. All we have left is an example that we will all do together. Thanks.